No? Let's try another one.
Can you do the clapping thing?
One. I think that's working.
Guys, slow it down for a sec. It's for a sec, all right?
No, for an hour. Yeah, go ahead.
For an hour. This is just how.
Yeah, so it's us, the Cyrex, and we're just here to let you know that tomorrow night is our post-return celebration. So at the common room, 6:30, be there. There's going to be karaoke night. And after that, it's probably going to be for an hour or an hour and a half. And then you can work on your physics problem sets, and we'll be there to help you. So,
Yeah.
there.
You there, guys.
Oh, yeah. Hi, so you
Yeah.
can all join us.
Yeah.
Okay, thank you, guys.
All right, thank you. All right. Karaoke in the anxiety room. Okay, all right. So I want to talk a little bit about Project 2 and the general framework for Project 2. And then we'll talk about dictionaries. So Project 2 is kind of what you've done in the lab 2 weeks ago now, except on a larger board. So the game is called Gomoku sometimes, or 5 in a row. So it's kind of like tic-tac-toe, but it's on a larger board, and you need to get 5 in a row. So usually it's played on a Go board. You can play it on paper too. So we refer to the things you put down on the board as stones because you play with Go stones, and it's white and black. So just for convenience, I kind of made it so that the W's are inside the squares rather than on the intersection. So same idea though, and that's the same as what you've done with tic-tac-toe, where, you know, if you want to put a white stone on 0, 0, then the white stone would go over here, for example. Right? So the basic idea is also the same as the idea for tic-tac-toe when you are about to win in tic-tac-toe, right? So like the way you've done it is you would try to put an X in each one of the squares, and then if that leads to your winning, then that's your move. Now, with games like, even like Gomoku, but like chess, like Go, stuff like that, it's almost never the situation that you're about to win. It's the situation that you might improve how well you're doing, right? So there are various approaches to how to do those things. So up until several years ago, the only approach that people knew how to really implement well was to look ahead, not just by one move, but by a lot of moves, and see, okay, like if I move like that, then my opponent could move like this, and then I could move like that, and so on, and eventually I'll win. So that's the kind of thing that worked really well in chess. So in 93, I believe, IBM's Deep Blue won against the then world champion Garry Kasparov in chess, using basically that kind of approach. Now, even that, so then in chess, you usually would not be able to look ahead until the end of the game. In fact, you still can't. So chess is known as what's called an unsolved game. Is this court complaining about something? No. So chess is known as an unsolved game. So unsolved means it's not known whether white wins with perfect play or not. Right? So another way of putting it is there is not a way to say this is the starting position in chess. Well, like, how should white move in order to win? The answer is, don't know. It's possible that if black plays perfectly, white is not going to be able to win. It's possible, though unlikely, that in fact, it doesn't matter what white does. If black plays perfectly, black in fact is going to win in chess, but probably not going to happen. Usually it's considered that being white is, and so playing with the white pieces is an advantage in chess. But it's not known. So why is it not known? Well, because you cannot say to the computer, well, just figure out, like, if white moves like this and black moves like that and so on, just figure out what's the perfect move for white. It's possible in principle, it's just that it's going to take a really, really long time to play it out, more time than a modern computer can actually reasonably be able to do. Right? So that's chess. So still, like, that's the basic approach. So what do you do if you cannot play it out until the end of the game? Well, if you know a little bit about kind of any kind of board game, you know that you don't have to exactly kind of say, okay, like, I'm going to play it out until it's a mate in chess, right? You can kind of see whether you are at an advantage or not. So you can say, like, what do I do so that no matter how my opponent plays, I'll be at an advantage in whatever, 15, 20 moves, right? So what does it mean to be, so how many people play chess here, actually? So not very many, actually. How many people play, like, anything like chess or Go, or like know how to play, I should say, rather than actively play, like chess or Go or something like that? All right, so not everyone. But everyone plays tic-tac-toe, right? So, or could play tic-tac-toe, I would hope. So the basic idea is like this. If you thought about kind of tic-tac-toe strategy a little bit, then you know that if you have a shape that's like this, then you're about to win, because O can block one of those, but it cannot block both of those at the same time. So this generalizes, as you know, if you know how to play chess, especially, generalizes to chess. You can kind of sometimes tell that it's this kind of situation where it doesn't matter what O does, it cannot block both of the ways in which X can win. So X is going to win in one move, unless O is about to win, I suppose. So in chess, it would be that you're at an advantage. Well, just if you have more pieces, and then there is kind of calculus about, like, not like derivative calculus, but like there is like computation you can do about how, you know, a bishop is worth like 3 pawns and stuff like that, right? So what you do is you say, well, like, using this kind of calculation, so in tic-tac-toe, it would be like, am I in a situation where I'm about to win in 2 ways and I can only be blocked in 1 way? In chess, it's kind of like that. So there's ways to evaluate the position. but also just it's called material. Like, do I have more material? Meaning, do I have more pieces, basically? And like some pieces are worth more than others. So in 15 moves time, am I going to be at an advantage in that way is a question that you can ask. And that's the way things have been going, both in computer chess and computer Go up until quite recently. So with AlphaGo, things changed a little bit in that AlphaGo, in addition to everything else, figured out how to evaluate a Go position, so a configuration on a Go board, really well. So AlphaGo, that's a DeepMind system, it does look ahead. It does try to game things out, but also even if it doesn't, it can evaluate how well you're doing, specifically in Go, so well that it doesn't need to. So how do you do that? Well, there's like a whole thing. You can take a third-year course and then a fourth-year course, and eventually you'll maybe understand it. But here's like a simple way in which you can try to do something a little bit sophisticated in Gomoku. So you can say, okay, so if I have a situation where I have a row of 3 white, for example, that's unblocked from both ends, so we call it open. Well, then I'm doing pretty well, because if I place another white stone here, I have a sequence of 4 that's open from both ends. So we term this an open sequence, and that means I'm about to win, because a sequence of 4 stones that's open from both ends, you can try to block from one end, but then you'll just move to the other end and you'll have your 5 in a row. Right? And that's good. Now, you're also in a good position if you have 2 semi-open sequences of 3, right? Because if you have 2 semi-open sequences of 3, well, at least one of them you can convert to a sequence of 4. Right? If you have 2 semi-open sequences of 4, so if you have a sequence that's, is it not sharing again? So if you have a sequence that's like that, and also another sequence that's like that, you're about to win, because your opponent blocks one of them and then doesn't block the other. Make sense? So what you can do is you can kind of say, okay, like, what is it worth it for me to have a sequence of 3 that's open? What is it worth it for me to have a sequence of 4 that's semi-open? So semi-open would be open from one end, so over here, but not the other. And then you can add all of those up and have what's called an evaluation function for any position that says how good or bad you're doing currently in the game. So if you're making an actual system, what you would do is you would use that in addition to kind of figuring out, if I do this, then my opponent does that, and so on. In project 2, what you're doing is you're just saying, if I place my stone in this position, what's my evaluation function say? If I place it in that position, what's my evaluation function say? And then you just choose the move such that the evaluation function is as high as possible. So the evaluation function specifically for project 2, I just gave it to you. It's this. So here, what you have is you have basically, whatever, like minus. So this is the evaluation function that says how well is black doing, and black is doing really badly if white has an open sequence of 4 or a semi-open sequence of 4, because we're assuming it's white's move. So black is trying. If I place black here, how am I doing? Well, if you left an open or a semi-open sequence of length 4, then you're screwed, right? So on the other hand, if you have an open sequence of black that's of length 4, then that's pretty good. So that's worth like 500 per open sequence of black. And then semi-open is not nearly as good because it might well be blocked if you just have the 1, and so on. Right? So that's basically what you're trying to maximize. That is given to you. So your job in this project is to basically count up how many open and semi-open sequences of each type you have on the board. That allows you to have an evaluation function. Once you have the evaluation function, another thing that you write is just a function that tries every possible move and finds the move such that the evaluation function is as high as possible for black. So basically it's set up so that the computer plays black and the user plays white. So the evaluation function always checks like if black just moved, how well is black doing? That's the project. Going back to kind of AlphaGo and stuff, how many people have heard of AlphaGo actually? Okay, so AlphaGo is the Google DeepMind system for playing Go that's used reinforcement learning. It does take kind of a couple semesters to explain, so I'm not going to try. But the basic idea is it figures out automatically this kind of evaluation function, but for Go. So for Go, it's much more difficult. If you know about Go, you know that kind of something silly, but just wouldn't work very well. So something silly would be, if you know how to play Go, just like count the pieces, like, do I have more pieces or do I have less pieces? Well, that obviously is not good because it's not just about pieces, it's also about territory. But even saying, okay, count up the pieces and the territory, well, that's still not that great because those things can flip very fast when you're playing Go. Getting more into the weeds of Go, if you don't know, just ignore me for a couple seconds. You can say, okay, like I'll count like how many eyes do I have? And again, like that's more useful, but you're not going to play very well if you just do that. You got to think about kind of more abstract things. So what AlphaGo does is it combines this thinking about what is my opponent going to do together with figuring out how to make an actually good function that tells you how well you're doing in Go. And unlike this, which I just wrote by hand, AlphaGo actually like figures out automatically like what kind of evaluation function is good. So it's you're not even telling it, okay, like you got to count like the sequences. It's not doing that. In Go, of course, sequences are not useful anyway. So something like that. Yeah. So I hope you enjoy this. So I sometimes do like tournaments for Gomoku. I think this year I probably am not gonna do a tournament for Gomoku. I think I'll just do a different one that's gonna be announced on Friday. Okay. So this is this. And now I want to do like the one last thing that you need to know about in order to complete the project. So some of you already started doing something like the project in the lab today. So the people who have the lab tomorrow will have that tomorrow. So I want to talk about dictionaries. So basically, a dictionary is a generalization of a list. So with a list, as everyone knows, you can have a list that's kind of like that. And you can access elements of the list using L at 0, L at 1, and so on. So dictionary is basically like that, except you can access elements that are not just at the index 0 or 1. The indices can be almost anything. So here's an example. So you define dictionaries using those curly braces. And it could be like grades. So it could be like that, like an ESC180, you got a 98. And then in ESC101, you got you got 100. And then like in Civ 102, you got 87. Okay. So that's how you define it. So you just say ESC180 corresponds to 98 and so on. You can then access those using grades, for example, at ESC 101. So that would be like this. So it's kind of analogous to saying like L at 0, L at 1, except you can, for example, use a string as the index. All right. So there a question on no? Okay. That's just jokes. So okay. In the context of dictionaries, the entries are called key value pairs. So this means that this is a key and this is a value. So a key could be an integer as well, right? So you could say something like LD is 0 is 2, and then 1 is 5, and then 2 is ASDF. And that would work exactly the same, right? So you could say, for example, LD at 2, and that would be ASDF. So keys are kind of equivalent to indices and lists, and values are equivalent to, the entries in the list. So the way in which this is the primary way in which this is useful is just something like this, right? So you want to be able to have kind of associations between keys and values. So if you remember, we already had this kind of problem, which we solved kind of awkwardly using lists, right? So we had this idea of usernames and passwords. And the way we did it before was to say like usernames are whatever. And then passwords are whatever. And then we just said like usernames at 0 corresponds to passwords at 0. So now you can do it in a more elegant way that's less error prone. Right? So like that's a way to do it. Like anything you might like to do with dictionaries, you can do this way. It would be slower and it would also be more error prone, right? So you could also say like logins is like this. Or 3987. All right, so that's the same. What are the ways in which this is better? Well, for one, it happens to be faster. We'll see why and how in ESC190. For another thing, it's less error prone, right? So like nothing's stopping me from having a username without the password here, right? Python is not going to stop me. As far as Python is concerned, it's just 2 lists. So on the other hand, if you enter it as a dictionary, there's just no way for you to make this kind of mistake. Python is going to yell at you if you try. So that's one advantage. Another advantage is that if you do it like this, there's nothing stopping you from doing something like this. right? So I just have two passwords now. So with so in dictionaries, keys are unique. Now, Python is not actually going to be upset with you if you do this kind of thing. It's going to say, okay, except it's the last one that counts if you do something like this, right? And the reason is clear, right? So if you say grades ESC101, well, that has one answer. You can't have two different answers there, right? What if there is a quiz? There is no quiz though. So okay. So okay. Yeah, there were like people leaving at the back. That's why I said it. Anyway, so okay. So that's kind of an exotic situation. Like in general, it's just that keys are unique. Unique, there's kind of no duplication. Right. So we'll see other uses for dictionaries as well. So far, it's just that if you store data that's not naturally associated with like indices like 0, 1, 2, 3, if it's not a sequence, then dictionaries make more sense. So dictionaries are also more convenient in that you can just add stuff to them. So you could say like grades ESC194 is equal to, what was the average? 70, let's say. I know what the, I don't know if it was announced here. So you can just do that. And now grades looks like this. Right, so that's completely fine. So with lists, you can do append, but you cannot say kind of at any random index that I want to add an entry. So in fact, that is why I use dictionaries in project 2. So in project 2, what you need to do is you need to say, is you want to be able to say like open W at 2 is like the number of rows of this length on the board. And it would be annoying, it's possible, but annoying to do it using append. So instead I just said, well, initially it's going to be the empty dictionary with nothing in it. And then I'll just keep adding stuff to the dictionary without having to worry about append. So dictionaries are also convenient in that way. So you can iterate through dictionaries. So let's take this. So you can do something like this. So you can say for subject mark in grades.items. This is the usual way that I would do it. So you would just say, put ESC180 in subject and then 98 in mark, and then put 101 in subject and 100 in mark, and so on. So that would be like this. So technically, you can also do something like for subject and grades without saying grades.items. And then you can say something. Like print subject. Mark is now, of course, not available, but you can say grades at subject. So that's, again, the same kind of deal. Almost always you want both the key and the value. So I would say almost always you want to do this. But this is something that you'll see quite often in code that other people write. Maybe you choose to write it as well. So that's a possibility. So notice that here I'm iterating over the keys, not the values, right? So I'm saying like so it's like subject is this, and then this, and then this. Iterating over values can be quite complicated. Part of it is you can of course get all the values, and I'll show you how. But part of it is that if you do something like this, that's completely valid, right? So keys are unique, but values don't have to be. You could very well get the same mark in two different courses. So if you go over the values, it's going to be kind of difficult to get the key back. Does that make sense? Okay. With that said, you can of course do it. So you could say for subject in grades. So this would be grades.keys, and then that would be the subject. You can get the mark as well if you do it like that. So that would be the keys. And then similarly, you could say for mark in grades.values. And this would be this. So note that I kind of take care to say for subject and grades.keys, for mark and grades.values. Of course, like I make up those names. This is just a variable. However, I strongly recommend that you do the same thing. So like name it subject, name it mark, and that just so that you don't get confused along the way. If you just name it something like X, that can be confusing. All right. So that's iterating. So one more thing you sometimes want to ask is a key, is the key there, is the value there? So you can evaluate it like that. So you can ask, is ESC180 in grades.keys? And that would be true because that's one of the keys. You can ask, is 87 in grades.values? And that also would be true. So similarly, you can just ask, is ESC180 in grades? That's the same as in grades.keys. So similarly, how you can say for subject in grades, and that's going to give you all the keys. You can say this in grades, and that's going to check, is that the key? So of course, not is that the value, so that would be false. Because it's not the value, it's just a key. All right, so let's do some kind of problem solving. Yeah.
Can you all the index of the value
actually, that's what I'm about to do. So yeah, good question. So let's say that what I want to do is exactly what you said. So want to get a key that corresponds to a particular value. So what we're saying is we're just having this, and we're asking, what course did I get 100 in? Right? So there is not a built-in function to do it. You have to do it manually. So this would be get key by value. And you can kind of see why there isn't a built-in thing to do it, because you now need to decide, okay, what if I ask about 87? You can't return, like there's two keys that correspond to 87. So one thing I could do is I could just say, okay, like get me a list. So that would be that the result is initially an empty list, and I'll just get a list of the keys. Right? So how would I do it? Well, I'll say, okay, so for K1, B1, and D.items. So that would give me all the key value pairs and D.items in turn. And I'll say if, in fact, this is V. So I'll say if V is equal to V1, then I'll append K1 to result. Then I'll return the result. Right, so K1 and V1 are like those key value pairs. So K1 is this, V1 is this, and then K1 is this, and V1 is this, and so on. And anytime that V matches to the V1, I say, okay, I got one of the keys that corresponds to V. Make sense? So now I can call it. So I do this, and I get the keys that correspond to each of the values, to kind of the given value. Make sense? Questions? So, okay. So the next thing you might like to do is you might like to say, okay, I just want to do it in general, right? So I want to get a dictionary where the old values are keys and vice versa. So the kind of thing that I mean is I want for like, so I'll call it, so this is sometimes called inverting a dictionary. So I'll say that the inverted grades are initially and an empty dictionary. So eventually I want it to be that 98 corresponds to ESC180, and then 100 corresponds to ESC101, and then 87 is two things, so that would be Civ 102 and ESC 194. Right, so that's what I want. So there's choices there. So I could say, well, like usually I wouldn't have replication, so I'll just make it a list if I have to make it a list. But that would be annoying because if I have to then go through this inverted dictionary, it's quite likely that I'll now have to check, oh, is it a list? Is it not a list? What do I do? Better to make it all lists, even if some of them are of length 1 or even most of them are of length 1. So how do I do this? Well, one idea would be I already know how to do it for one value, so I'll just do it for all the values. Right? So I'll say inverted dictionary, D. So I'll say result is initially empty. And now I go through all the values, and for each of the values, I get the keys by that value. So I'll say for V in D.values. So get all the values in turn. And I'll just say result at value is all the keys that correspond to that value. And I already know how to do that. And that's fine. That actually works. Now, you'll notice that this does a little bit of extra work that maybe I don't need to, because if I have the same value repeated every time, well, it's just that I'll get the list of keys that correspond to 87 twice. But that's okay. I'll just say, if I've already added that to the dictionary, I don't need to re-add it. So I'll say if V is not in res, and I'll specify res.keys, then I do this. If V is already in res, then I already done this. So don't need to compute the exact same thing again and put it in res V again. So note that I said this is a value, but I'm asking, is it in res.keys? Well, that's because it's a value in D, but it's a key in res because it's inverted. Make sense? Yeah. Yes. So dot keys is for iterating over keys. So those are the keys. Dot values is for all the values. So those are the values. Items is keys and values together. All right? Yeah. Why I added? Well, it's just that if I don't do this, then V, in fact, so like I was worried that like V would repeat more than once. Right? In fact, it won't, so it's fine. So okay. So that's how you do it. So I want to note, so we've done nested loops quite recently. And as you might remember, we had this structure where you could have a helper function instead of having a nested loop. This is one of those situations, right? So I could say, well, I want to write it as just one function. So here I would say, okay, all right. What I want to do is I now want to go through all the possible keys in D, and if the D is there, I'll add it. So how do I do it? Well, I'll say, okay, so V is in D values. So initially reset V is going to be nothing. And now I'll go through all the possible keys. So I'll say 4K1 V1 in D dot items. If the values match, then res V gets K1 appended. Right? So that's the same. And that looks now like a nested loop. Right? So all a nested loop is always is just basically, you could say the inner loop is like a function. It's just that instead of this, I just copy and paste basically the body of this function inside the nested loop. Does that make sense? Questions? All right. So one last thing I want to do today is called tuples or tuples. So some people say tuples, some people say tuples. Those are both valid pronunciations. So the way you write a tuple is like this. So it's like a list, but in round brackets. You can access elements of a tuple like this, like with a list. So the only difference is that you cannot change the contents of the tuple. right? So you cannot say t at 0 equals 1, 2, 3. That would be an error. So we in fact have seen tuples before implicitly. So you can unpack tuples. So you can do something like this. And what's gonna happen is A is the first element, and then B is the second element, and so on. So that is in fact what's going on when we had done swapping by using multiple assignment. So when you say something like XY is 10, 12, in fact, what's happening is 10, 12 is a tuple, and then that tuple gets unpacked into XY. So that is why you can do something like XY equals YX. If you remember, the problem initially was when we were trying to do swap without temporary storage, is like you place Y and X, well, now you lost the value of X. So how does it avoid it? Well, it doesn't. It's just that YX is actually like a separate thing. It's now a tuple, and then that tuple gets unpacked. So in that way, you're not actually not using temporary storage, you're just hiding it away. So that's one interesting thing about tuples. So similarly, if you're returning two things from a function, and you say something like this, that works. So A is going to be 1 and B is going to be 2. Why does it work? Well, because when you're doing a return, when you're doing an assignment, you don't have to have the round brackets. What's happening is you're returning a tuple and then you're unpacking it. Make sense? So that means that you can do something like this. And T is now just going to be a tuple. You can unpack it later, or you can do something like T at 1, and that's going to be 2. So one last thing that's interesting about tuples and dictionaries. Keys in dictionaries have to be what's called immutable. So just objects whose contents you cannot change. So tuples, integers, strings. But not lists and dictionaries of the things that we saw so far. And it makes sense that you wouldn't be able to use mutable stuff as keys because like you change the contents of the mutable object. Well, like how are you going to use it as a key? Makes no sense. However, you can do something like this. This is completely fine. I'm not sure if we have a dictionary. We don't have a dictionary here. But you can do something like D is 5, 6. And then that's ABC or whatever. And that wouldn't work with lists. But it would work if you make it a tuple. So something like this. And then you can access the ABC like so. All right, 5 o'clock. See you Friday. Bye.